Okay, so extreme values. Anybody know? Justin knows. What's an extreme value? Oh. Well, then it's good that we're going over it.
If f is good to choose a closed interval AB, then f takes an absolute maximum value of c, and f gives x value f at some number. Where did you find that? Yeah.
Some, math books are not easy to read. Okay, guys? So even I have sometimes hard times reading these, but you're going to have to learn how to do that because they're going to expect you to read your book next year. An extreme value, you're going to be in trouble, is a maximum value of the function or a minimum value of the function. Hey, Justin, that's what it is. It's the maximum value of a function or minimum value of a function. So when they ask you to find the extreme values, that's what they're talking about. If they don't say local or relative, they mean an absolute maximum or minimum. So if they say find the maximum, it's the absolute. So the absolute max is the largest. Now the local ones are relative. They'll say one of those words. That's in the largest, in the neighborhood. I look at it this way. It's like, I think I'm spelling that right. Oh, we could do Halloween decorations. Or maybe I'm the only one that does it. Or holiday decorations. You know, you can have the best decorations in the neighborhood, but they might not be the best decorations. Now, I got to make one thing a little bit clear, and the author is actually not correct. Okay. This is just some function. And the absolute max and mins can occur at the endpoints. Actually, the locals can. I know. I know. I'm explaining that to you. According to this textbook, they can't occur at the endpoints. And we're not going to look for local and relative max and mins at the endpoints. But when you get into the upper level mathematics, and the reason why I know is I was on the listserv and I asked about it. But yes, local max and mins can occur at endpoints.
That makes sense.
I don't think it makes sense because when you're looking at a neighborhood, you need to look at both sides, neighbors on both sides. So this is the relative max.
So could there be a hole?
If there's a hole there, is there a relative max? Is there an absolute max? No. Nope. Because the point doesn't exist. So you can say, I'll take this point right next to it, and I'll take that point and the one that doesn't exist and average them. I can always get close as I want to that hole. You can always get closer yet. It's infinitely small. So there's no max here. That's right. Okay. So in this textbook, the author does not consider endpoints. See, how do you know if that's a minimum or a maximum? Yes, I can look just to the right. And I suppose in that context, yes, it is a local minimum. But maybe that's what the function was doing coming in there. I don't know. Right. Well, but in the real mathematical world, we can have local maximums at the endpoints. For us, we're not going to look at endpoints for locals. It won't happen. They will not end up with a situation where you'll be looking at that.
Correct.
Yeah.
Unless it's a flat line.
Well, then it's both, which is a trivial case. Okay, so, and this is going to be my absolute minimum. No, we're not going to use our endpoints in this course, but in your future math classes, if you go on, evidently, I don't remember that from college, but you can have them. You can have local ones at the endpoints. Okay. Was the max-min existence theorem in this section? The book is a little bit different order than the other one. Yes, the extreme value theorem. What about that one? Yeah, do you remember the extreme value theorem? This is a very important one. Now, it's probably more important in AB than it is in BC. It's usually the first or second question in the AB exam. And sometimes it's the common question, but I'd say most of the time it's not. What are the conditions for this one? You have to have a continuous function. Okay, Justin, you need to sit someplace else. Focus. It has to be on a closed interval. And that's good that you wrote it, but you know what it says? That's the big question. Then, this extreme value theorem guarantees, this is a guarantee, I love guarantees, that you will find both a max and min. You'll need it for optimization problems. Both a max and minimum value of the function, not the x-coordinates. That's not what they're talking about. They're talking about the max minimum value of the function, that's the y-coordinate, will exist. Well, it's nice because you get to the exam and they say, find the point that's furthest, I don't care which direction, you know you're looking for a max or min, or it'll, when is your profit, or what is your maximum profit, something like that. It'll say that. You'll see it's a continuous function, it's a closed interval, and now you know this is easy to find the max or mins, because do you remember where we look for them? Okay? These, yes? Can be. You're talking about horizontal line? Wait. Like this? Oh, like this? No. There's no max, no min.
No,
He's.
I was making sure. So I felt like this could be on a shoulder.
Okay, guys. Where do your max mins occur? Endpoints? There's no calculus to get an endpoint. F prime is 0, or F prime is undefined. Okay, ready? Oh, that was sloppy. Let me fix that. Oh. Okay? These are the only places where you can look for a max and min. These are what I call candidates. And now as we're looking at the Republican primaries and caucuses and stuff, Justin, these are the candidates. Not everybody's going to win. Not everybody's going to give a max and everybody's going to give a min. Michelle Bachmann dropped out because she was the min in the last one. Okay, how do you know? Okay, guys, so we can get this done and you can have work time. Shh, Justin, Mr. Bader. Listen to the videos because you're going to hear his name a lot, right? Okay. How do you know, guys? How do you know you have a max or min? How do you know which one it is? You evaluate f of x at the endpoints, and I'm going to actually just call these the critical points because people get confused, and I think that's better. And the critical points. And then you see which is the biggest, which is the smallest. The only calculus involved is to take the derivative and find out where the derivative is 0, or to find out where the derivative is undefined. And that's just division by 0. That's it. That's the only calculus there is. Now, I think I hit on the most important things. You're not going to have to know Fermat's theorem. No.
Oh, yeah, we have to write
Well, it's in the reading. It doesn't hurt you. Okay. Nice job. Now, let's get into this next section. What do we know about derivatives? Derivatives are going to tell us a lot. But there's this mean value theorem, and I posted a link on Schoology. It talks about a court case, and they actually use the mean value theorem. They actually use calculus. Yeah, go look at the link and you read about it. It took them like several months to resolve the legal issue. I think it was a guy speeding. The same.
Oh, wasn't the lady that killed her daughter and put her in the car in the car? What?
I don't think that's the mean value theorem. Now, do you remember the mean value theorem?
Yes.
And you can call it MVT. Yeah. Might have been with a, I don't know. I don't remember anymore. Differentiable function. Now, if you have a differentiable function, what has to be true about the function? Has to be continuous. Okay. Now, what this is saying is, let me draw a picture of this. And if you have a continuous function, it's differentiable on the interior, not on the exterior, it doesn't really matter. And here's my function, here's f of x. And I'm going to take a couple points on here, call that A, call this one B. Then the ordered pair here is A, f of A. And this is B, f of B. And if I draw the secant line, you remember that?
Oh, yeah.
That's the secant line. Then someplace on this curve, no, I don't want that, I want this. Okay, maybe that's what I'm going to have. Okay, the slope of this tangent line will be equal to the slope of the secant line. And that's what it's saying. The slope of the tangent line is the derivative. So they're saying that right here, this is the instantaneous rate of change. And this is, what's this called? What's the slope of the secant line? It's also called the average rate of change. We can't forget any of this stuff. And we'll have the mean value theorem for integrals. And I'll connect them. If you didn't see the connection last year, hopefully when you see it again this year, you'll see it. Matt and Justin. Okay, if you just multiply both sides by b minus a, you get this line. That's another version of the mean value theorem. I needed to prove the fundamental theorem of calculus. Can't do the fundamental theorem of calculus without that. I've never proved it to you. We can if you want to this year when we get there. It's kind of up to you guys. It's an interesting proof, and it involves collapsing sums. That's what's kind of cool. Oh, but I'm not asking you to repeat it. It's just kind of cool to see it. It should bother you why the fundamental theorem holds, but anyway. Okay. Now, if the function's not differentiable on the interior, then the mean value theorem does not apply. So your first thing you have to do is always see if the mean value theorem applies. Is this a continuous function on a closed interval?
Yeah.
And it's differentiable everywhere, right?
Yeah.
So here's what you have to do. You have to find g prime of c, or you want me to just leave it as x? I prefer to leave it as x. Equals, well, that's 3x plus 1 to the second power times the derivative of x plus 1, which is just 1, has to equal g of 1 minus g of negative 1. I'm just going to find the slope between those two endpoints over 1 minus a negative 1. Is that okay? And so I'm going to get 3 times x plus 1 squared is equal to, what's g of 1? Well, I could have drawn it too. It's 8, and negative 1 is 0 over 2. So 3x plus 1 squared is equal to 4. Now I could square all that out and then factor it and all that stuff, and I don't want to do that. Because I can make it easier than that. I'm going to isolate the squared term. I'm going to divide by 3. So I end up with x plus 1 squared equals 4/3. And then how would you get rid of the squaring? Square root it. Now be careful. This is 2 over the square root of 3, or you could have just left it. It doesn't really matter. But what's the left side? It's the absolute value of x plus 1. Whoops. Well, it's important because square roots are never negative. So how are you going to get the other answer? There are 2 answers here. One we're going to throw out, though, I think. So x plus 1, whatever you, remember we're trying to solve, and whatever I solve, I have to do something that makes the equation true. So I could put a 2 square root of 3 in there. That's going to be true. But I could also put in a negative. That's also equal to positive 2 over the square root of 3. So on this one, as x is equal to 2 over the square root of 3 minus 1, which I believe is positive, or, and this one's clearly negative, negative 2 over the square root of 3 minus 1. And that's negative. And what was my interval? Negative 1 to 1. Oh, I better draw the picture of this. It's not this one. Actually, that is negative, I think, isn't it? I don't know. I don't remember. Remember what this looks like? That's straight. Good. I can't stand it when it's not straight. If it's x plus 1 cubed, and it's shifted. So it's going to look, here's x cubed. Now I'm going to shift that. I'd prefer to do it that way. There it is. And I'm going to go from negative 1, which is 0, and positive 1, which is like 8. So this is the secant line, and there is the tangent line. There is another answer over here. However, it's not in my interval. So I have to throw out one of them. This one's smaller. So it's got to be that one. I don't know what it is, but you can put it on a calculator and find out. So mean value theorem is not too hard. And if you think of this, if this is your distance, if this is your position, then this is saying your average velocity equals your instantaneous velocity. So if your average velocity is 85 miles per hour, that means somewhere, sometime, you had to be going 85 miles per hour. And that's how they can get you. If they can measure your distance and time, and they can find your average speed, and if your average speed is higher than the speed limit, you're guilty of speeding. Yeah. But they don't have that technology so much anymore because they have other technologies. I don't think they use that. Well, Indiana Toll Road they could, because you get a card and it gives a time stamp and a position stamp.
No, it's all wrong.
Indiana's Toll Road.
We just drove back on it.
Did they get rid of the toll road? Interstate 80 is a toll road.
No, we're on 65.
Yeah, that's north-south. This is east-west.
Come on.
Well, they could have gotten rid of it, but I can't imagine our government ever getting rid of a toll road. They're expensive. Okay, let's do this one. Wait, what happened to example 2? Oh, are you guys in the right order and I'm in the wrong order? Let's do example 2. I like to do example 2. It's easier, a little bit easier than example 3. Okay, you guys? Got to have a continuous function on a closed interval. I've got a closed interval. Is it continuous? It's continuous on other intervals, but it's not continuous on here. So it's not continuous at x equals 3, which is clearly in our interval. Therefore, mean value theorem does not apply. You know the 3 little dots means therefore, right? Okay. Okay, what about that one? I have a continuous function on a closed interval. In fact, if I graph it, cube root of x looks like this. Here's negative 3. Here's positive 3. Now, just because the theorem doesn't, you can't invoke the theorem, doesn't mean that the theorem doesn't, I mean that you can't find the average and the instantaneous and have them be the same. It's possible. There's just no guarantee. That's all. What's the problem with the origin? It's a vertical tangent. So is it differentiable on this interval? So if I do f prime of x, what is that? This is x to the 1/3. It's 1/3 x to the negative 2/3. Whoops, x can't equal 0. Okay, so it does not apply. Because you have division by 0, because this is 1/3 cube root of x squared. Okay, does not apply. It's not differentiable. Now, that was on the exam last year. I think it was last year. On AB, and you had to say whether or not it applied. And we did well on that question, I think. Not differentiable at x equals 0. I can get stats on them. This year, we're going to be ordering the exams. So if you guys want to come back in the fall, you can look at your exam. But I want to look at them because I want to see what it is you missed. Now, there's no writing on your exam. We're not allowed to write on the exam. We just have scratch paper and we take our little notes and then we bubble in what your score is. There's nothing written on your exam. But knowing that, especially since I read it, and I hopefully be reading BC again, I can go back and reread your exams in the fall when I get them. And I can see where the mistakes are. What am I missing? What am I not giving you? See, I think it's very powerful. I wanted to get them last year, but I didn't. Okay. Is that it, or is there another one? Oh, let's do this one more time. What if we change the interval? What if we just go from 0 to 1? Remember, it only has to be differentiable on the interior. Guess what? This one works. It does. So let's do this for the algebra. It's a closed interval. It has to be differentiable on the interior. And this is differentiable on the interior. We have our derivative right up here. It was 1 over 3. I prefer to see it in radical form. Cube root of x squared. That's going to equal f of 1 minus f of 0 over 1 minus 0. So it's 1 over 3 cube root of x squared. Justin, what's f of 1? It's cube root of 1, which is 1. And 0 is obviously 0. This is 1. How do you solve for x? It's a proportion. See cross? Yeah. So when I multiply these together, I get 3 cube root of x squared, guys, equals, and I multiply these together, I get 1. And again, just like I did with the squaring, I'm going to isolate this cube root. So it's the cube root of x squared equals 1/3. Now how do I get rid of the cube root? It's the opposite of cube rooting. Cubing. And so I get x squared equals 1/27. And now when I square root both sides, I'm going to get 2 answers. Because one's the other side, the negative side. So amplify of x is equal to 1 over, 1 over the square root of 27. And you have 2 answers. X is equal to the positive, and I don't care if we change it to radicals or not, it's unimportant. The only time it would be important would be matching on the multiple choice. Now, do you remember the mean value theorem? Me back? Right, it's not going to be the negative one, because that would be the other side. The difference is this went from -3 to 3.
Like 2 over square root of 3 minus 1. You got that?
Yeah, don't do that.
Back up.
Okay, what was your other question? No, there was somebody asked another question. About the first page. Difference between what?
Like, when it was 2 over square root of 3 minus 1, how did you decide which one to use? Which one?
Oh, I have to look at my interval. So you'd have to actually use a calculator probably to find out exactly what that is.
You just
I just knew that this was more negative, and I looked at my picture and I said, well, this is probably positive actually, but
okay.
yeah, that's a little bit bigger than 1. It's not very big. 0.1 something. Okay, little more and we're done. Whoops. Now, a function that's either always increasing or always decreasing is said to be monotonic. I don't think they'll give you that word on the exam, so I don't think you have to worry about it. Now, what does the first derivative tell you? If symbolically, I'd rather write it, if f prime is greater than 0, then f is increasing. If f prime is less than 0, I may have some typos here, then f is decreasing. Okay, do you remember that? That's called the monotonicity. No, that's the next one. The concavity test. Concave up like a duck. You're happy. F double prime is positive. as a reader, I prefer to see that than sit there and saying f prime is increasing or decreasing, because then I have to sit and think, okay, what does that mean? This is the easy way to do it. And if it's down like a frown, f double prime is negative.
You put the little eyes on there.
They'd probably find it cute, yes. But what's your justification? Your justification in your problems are saying this. You don't have to make it a big essay when you justify these things. Why is it a max or whatever? Because the second derivative is negative, so the function's concave down. Keep it simple. Because if you get it too wordy and we don't understand what you're doing, it's going to be wrong. Okay, you remember inflection points?
When that double prime changes signs.
You have to actually do it. Yes, probably. Depends on who it is, actually. Okay, do you remember inflection points? Be careful. Inflection points definition is where the concavity changes. Okay? But that's not the proof. The proof is the second derivative must change sign. If the concavity changes, that's just definition. Okay, guys. I'm done.
Say, Kevin.
Okay. Candidates. Now, there's candidates, you guys, are when the second derivative is 0 or undefined. That doesn't guarantee that you have an inflection point. If the inflection point, actually, it's a... No, I won't say that because not true there. Local max and mins. Do we know those? All it's saying is you have a local max if this y value right here at C, if that's bigger than everybody in the neighborhood. Bigger value. Same with the minimum in the neighborhood. And was that it? I just said that f of C, this y value here has to be bigger than all the other y values near it to be a local max. This is a long one. Because then I think tomorrow's a work day. You got some tough problems in there. Or it's in 4-2. Okay, ready? Do you remember the first derivative test? This is repeated. Okay, guys, first derivative test. Now, you get no points for drawing the line graph. And I don't memorize it, I just look at the picture. It says the first derivative will be 0 or undefined. If it's 0, then you're guaranteed a smooth transition. If it's undefined, it could be discontinuity, and it could be a vertical tangent, or it could be a sharp corner, or a cusp. And if the derivative goes positive to negative, then that just tells me my function is going to be increasing, then decreasing. This is what this means. Therefore, I have a what? Local max. So how do you justify it? You say you have a local max because f prime goes from positive to negative. They don't care if it's 0 or undefined at that point. You just want to know if it's max. Like absolute value function. The derivative does not exist at this point right here, but it's still a max. Okay, what about the local minimum? What's that going to look like? Okay, so if this is f prime, and if this is negative and this is positive, the function is going to decrease, then increase. So f prime changes from negative to positive. And then they get you on the second derivative test. We've reviewed that, actually, because we did it in Taylor. Change of sign. Now, the second derivative test, you have to find the first derivative, and you find where f prime is equal to 0 or undefined. And then you find the second derivative, and you evaluate it at those critical points. And if the second derivative is positive, right? That means my function, because I don't have this memorized. What does it mean? It's concave up. Therefore, it's a max or min? Yeah. And if the second derivative is negative at that point, you guys, Justin, it's concave down and it's a max. You have a problem when the second derivative is 0 at that point. If I take y equals x to the 4th, I know it looks like this, right? There's some idea it looks like that. It's a minimum, right? What at 0 in particular? What's the second derivative? First derivative is 4x cubed. Second derivative is 12x squared. So guess what? Second derivative is 0. What do we know? We know nothing. Let's look at this class. Let's look at x cubed. That was Hogan's Heroes. Hogan's Heroes. I Know Nothing is a TV show. Yeah. Here's the cube. Hogan's Heroes. Okay. The guard is always knows what Hogan's Heroes are doing. This is World War II, and they're in a prisoner of war camp. And he always knows what they're doing. They're always doing bad things, naughty things, because it's a comedy. And he would always go to the colonel and say, "I know nothing," but he always knew, but he would always pretend he didn't know. And he'd go like this, "No, I don't want to hear," because they break out of the camp all the time. Okay, let's look at the first derivative here. It's 3x squared, obviously critical point at 0. Second derivative is 6x. What's true about the second derivative at 0? It's 0. So here I have a minimum. Here I don't have either. Second derivative being 0 tells you nothing. You have to do a first derivative test. Second derivative test fails. If the second derivative is 0, at that point, it could possibly be an inflection point, might not. When the second derivative is 0 and you're testing for max and mins, when the second derivative is 0, then you don't know. You know nothing. You have to do a first derivative test. Oh yeah, what's the slope of a line? Everything's a max min on a horizontal line. Okay, so second derivative test fails. If y double prime equals 0. We just had what? Did you get it? I think that was it. I'm hoping. Oh, just a little example. Why don't you guys try it? Yeah, let's do this. And then we'll finish up class. Tomorrow will be a work time because I've done everything today. So now the page number is not right, the problem number is not right, but it may be a homework assignment, I don't know. Okay guys, how do you find where a function is increasing or decreasing? Okay, it's the algebra that is going to get you in trouble. So what's f prime of x? Okay, I want to know whether this is positive or negative. Okay, Justin, how do I do that? We set this equal to 0. 4x cubed minus 12x equals 0. And to find the zeros, I'm going to factor. Factor what? Let's do a 4x. X squared minus 3. Did I do that right? You have 3 critical points. You've got 0. And don't forget, even if you're looking for one where it's division by 0, don't forget to include that because it'll mess up your testing graph. Okay, this is f prime. And if I put in 100, because that's certainly big enough to the right, I always use factored form because it's easier. That's positive, that's positive. What's some number between 0 and the square root of 3? What did you say? What about 1? Is that positive? That's negative. What about negative 1? Negative 1, this will be negative and this will be negative, so it's what? Positive. What if I do negative 10? This is negative 40, but that's positive, right? These are the split points. So that was negative. So what does it tell you, Matt? Matt, what's it tell you? The function's what? decreasing, increasing. Zero's on my function, so I'm okay. Increasing, decreasing,
It's
increasing.
like a sine word.
No, it's not. It's an x to the fourth graph. It's like a W graph. How's that?
So it's because it's 4 times. Touches X 4 times.
I don't know where it is.
It has to
This is the shape. Remember, it can be shifted up or down. It's just the shape. So where is it increasing? It's increasing from negative square root of 3 to 0. And now, if you want to close intervals, that's fine. They're not going to look at it. And it's increasing from square root of 3 to infinity. Find the local and maximum and minimum values of the function. Okay, guys, how do you find the maximum value of the function? It's not asking where, it's asking what. So where are the max? The max occurs at what? 0, right?
Right.
So f of 0 is equal to 0.
0. And that's because it's plus positive.
All I do it because it went positive to negative, so that's a max. I could do a second derivative test too if I want. Should we do a second derivative test? What's f double prime? Here's f prime. What's f double prime then? 12x squared minus 12, which is 12. Well, I don't have to do that. I just have to evaluate it. So what's f double prime of 0? It's negative 12. So that means the function is concave down. Is that a max or min? Okay, we could do the same thing with the other ones. You either have to justify it with a first or second derivative test, though. What are the minimum values? I have to actually evaluate f of the square root of 3. Now I'm going to take square root of 3 to the 4th power. What's that going to give me? You guys clever? Well, it's square root of 3, square root of 3, square root of 3, square root of 3.
It'll be 9.
That's 3. That's 3. And that's 9. 9 minus 6 times 3. So it's what? Negative 9. Once I know that, I know where to place my graph. I'm not finding the zeros of the function. I'm finding where the max and mins are. And it says, find the intervals of concavity. We could do that. They're asking for it in particular, but I'm telling you, if they didn't ask you those questions, you already know what it looks like, because I told you, if this is a 0, it's going to be smooth. No abrupt changes, no sharp corners. So I want to find the inflection points here. How do I do that? Justin, how do I do that?
Beta.
Okay, f double prime is equal to 12 times x squared minus 1. Inflection points occur where there's a sign change. The candidates for a sign change are what? 1 and negative 1. And you got to check. Now, I like to be efficient, and I don't want to put in numbers because I don't need to. I know this looks like a parabola. This is a second derivative. So I could just do a little sketch, and it looks like this. This is plus, this is minus, this is plus. Do we have any inflection points? Yeah, we do. How many? 2. There's an inflection point and there's an inflection point because f double prime changes sign. We also know the concavity too, don't we? This is concave up, concave down, concave up. Notice I really didn't need to do that if I wanted to draw a sketch because of the zeros. There it is, concave up, concave down, concave up. If there's 0, we're okay. And then it asks for what? Check your work with the graphing calculator. Perfect timing. Okay, 4-1 should be turned in today.
Oh, I already put it in my backpack.
No, you don't have it, huh?
It's